Section 10, signal circuit integrity testing. We've done some of this in section 7, which was potentiometers, so some of this will be a repeat, but there are some other areas where we can do this type of testing. And again, the purpose of this is to prevent us from having to do ohm checks on the harness. And just about every engineer-written flowchart, when you're checking sensor circuits, are going to have you disconnect the sensor, disconnect the computer, and measure wiring for opens and shorts. And that is very time-consuming on a lot of cars, especially where the computer lives. So that's the purpose of this, is to avoid having to do that procedure and save time, and it's also very accurate too. So starting on page 2, kind of giving you that description on what I just said. And this is going to prevent the need for us to have to unplug the computer. And that doesn't really sound like a big deal, but where some of these computers live inside the car is not easy to get to. So we don't really want to do the ohm test when we can get away with it. So what we're doing, opens and shorts in a circuit, in a sensor circuit, that's the purpose here. Page 3 would be using diagnostic trouble codes to do this. And truthfully, I remember first doing this procedure, and I need to give a Ford engineer some brownie points for a flowchart that I read. And on the early Ford designs, it was common to not have data stream. All you were able to do was to read trouble codes on these systems. And I remember reading a flowchart where I believe it was on a map sensor or something like that. The trouble code was map circuit low. And when you went through the flowchart, it would have you disconnect the map sensor and jump the signal to the 5-volt reference. And then what you would do, again, we have no data stream to look at, so that's the perspective here. Right? And we need to check the integrity of this circuit before we replace the map sensor. And what you would do, you jump the 5-volt ref to the signal, and then you clear the trouble codes, and then you rerun the key on engine off test, and what it should set in the process is a map circuit high trouble code. And after you did that procedure, if it changed from low to high, then your circuit integrity is good. And so I actually developed this from an early flowchart. You know, I'm always against flowcharts, but, you know, not all the time. I've certainly learned a lot from them. Do you understand that what we're doing on this page would be on a vehicle that does not have data stream? Yesterday we did a 1991 Eagle Talon, Mitsubishi Eclipse. On that particular car, we had manual codes only. This would be a prime candidate for a job like this, or for a testing method like this. You have a trouble code and it says circuit high. In the name, what we're going to do is we're going to pull the circuit low and reread the codes. Make sure it says circuit low. If it stays circuit high when you're pulling, say, a signal to ground, then you have a wiring problem, not a sensor problem. If you have a circuit low trouble code, what we want to do is we want to pull that circuit high. And if it stays low when you pull the circuit high, then you have a wiring problem. You don't need a sensor, and that's the point with this page. Okay? So we really don't use this one on today's cars, because most of today's cars, OBD2, we have data stream that we can use. There are certain data parameters, though, that might not be given to you. If all you have is a global OBD2 scan tool, there are certain data parameters that you're not going to see. An example might be a GM system that has a fuel tank pressure sensor that's used for the evap system. You're not going to see that data parameter on a global scan tool. It's just not going to be available to you. You need a factory scan tool to see that PID. So that might be something that you could do on an OBD system. I think one of the things, though, that we want to be aware of on an OBD system is that two-trip detection. And what two-trip detection means on OBD2 is it needs to see the fault 2 consecutive times before it sets a trouble code for it. And unlike OBD1 or pre-OBD2, where it would flag it right away, OBD2 systems, two-trip detection. So you might have to start the car, shut the car off, wait a few seconds, restart the car for that code to set. But I'm generally not doing this on an OBD2 car. I'm generally doing this on an older system that I don't have the ability to look at data stream, and all I can get out of it's trouble codes. You know, you can even do this on a vehicle that doesn't support scan data connection at all, and you're using flash code diagnosis like we did yesterday. We had a code 14 on that Mitsubishi Eclipse or Eagle Talon using a flash code method. You can do the same type of thing. And so again, the purpose of this is to prevent us from having to, you know, if we're dealing with a map sensor and it's a 3-wire sensor, it goes to the computer. Of course, we could have a map problem, we could have a wiring problem, we could have a computer problem, and what we're attempting to do is to address the wiring from the map sensor to the computer and the computer itself with this test. If this test responds like it should, it allows you to accurately say, okay, you need a map sensor. You know, of course, there's a few other checks we're going to do too. We're going to check our reference and ground, but the signal circuit is the primary focus, and it allows a quick diagnosis of that. So to review what we've done already when we talked about potentiometers, throttle position sensors, where if we have a circuit high code, that means the computer's seeing probably 5 volts all the time on the signal circuit. It is completely safe. You're not going to cause any damage to a computer because it's just a sensing circuit if you were to jump that circuit to ground. So let's just get a little perspective here. Let's say that the picture we're talking about, the computer is seeing, in this sensing circuit, it's seeing 5 volts all the time. If you unplug the connector and you ground this signal wire, that should pull this 5 volts to ground, and that sensing circuit should see 0. If that occurs up here, what's going to happen, you had a circuit high code, it should now switch to circuit low, and that tells you what about the integrity of the signal wire. No opens, no shorts. You're good. Circuit low trouble code, a little bit different. Our circuit low code, computer is seeing not 5 volts all the time, it's seeing 0 volts all the time. So what we want to do is we want to unplug the sensor, and remember that some designs, because of an internal resistor, just unplugging the sensor causes the signal voltage to rise to 5. Reread your trouble codes. You should now have a circuit high code. If it's not at 5, you're going to take a 5K ohm resistor and jump the circuit, which should change this to 5. The computer should now see 5, and it should set a circuit high trouble code. If it sets that circuit high trouble code, how is the integrity of the signal wire, which is our primary concern here? It is good. We got no opens and no shorts. Why are we using a 5K ohm resistor? Just in case the signal wire is shorted to ground, so we don't pull the reference wire to ground through the signal. Our 5K ohm resistor will protect us from that. So that's our circuit high, circuit low trouble codes. Something else down here when we're doing this is, I mentioned the 2-trip detection, but there's one other thing that you have to be careful of, and I got burned on this on a map sensor. I was doing an integrity test on a map sensor, but I was using scan data, so we'll jump down here. And I have the same note here. The engine may need to be started for an update to take place. So let's say you're looking at the map sensor on scan tool, and I see map voltage, and it's at 0 volts. That's a problem. We have a trouble code for the map sensor. So I'm doing this test, and I unplug the map, and I'm taking that signal wire, and I'm jumping with my resistor, this 5K ohm resistor. Again, we're looking at scan tool connected. Map was at 0. What we want to see is this map voltage jump to 5, right? And the map voltage on this particular car stayed at 0. And so my concern was a wiring problem. That's the whole point of the test. So I took my voltmeter, and I wanted to make sure that my resistor was okay and that my test was valid, and I measure my voltage here, and it's at 5. So I take it further. I'm thinking I got an open in that signal wire. Does that make sense? That's really what the test is for. So I move my voltmeter down to the computer, and I have 5 volts at the computer too. So I don't have an open in the signal wire. On this particular car, for the map sensor, initial key on, the computer will look at the map sensor to see what it's reading, and then it looks away from it until there's an RPM signal. So what I'm telling you is when I was doing this integrity test, I needed to crank the engine over to get that map data parameter to update. There was nothing wrong with the wiring. All I needed to do was crank the engine over, and as soon as I cranked the engine over, this went from 0 to 5. So I'm warning you, when you're doing integrity type testing, which I'm teaching you, you may have to crank the engine over and have an RPM signal for some of these data parameters to update. So I wasted a lot of time on that car, didn't I? I would have been better off following the engineer flow chart to own the wire, right? Or maybe been a parts change and just threw a map sensor at the car because that's what it needed anyway. You know, and a lot of this stuff, when you got fixed 0 volts, fixed 5 volts on a sensor, most of the time it is a sensor, but, you know, it's not about being 85%. We want to be 100%. You know, 85% of the time it's a bad sensor, but we want to be 100%. And these methods are very quick if you understand how to use them. So that's what I meant right here by this engine may need to be started or at least attempted to start to have that data parameter update. All right, so we've already talked about this one, potentiometers. This was section 7. I had info in there on that. Section 7 was potentiometers. We did this part already. Disconnect the sensor, check the sensor pin. Jump the reference to the signal wire using a 5K ohm resistor. We're doing all the same stuff. Again, this step's not needed. On some, look for the sensor pin to change, and that's just simply down here on this page. And again, on some of these designs, what it is completely normal when you unplug the sensor to see these numbers here. And on other designs, it's completely normal to see this. So if you're fixed at 0 and you unplug the sensor and it goes to 5, you're done. You need a sensor. It's shorted. If you're fixed at 0, you unplug the sensor and it stays at 0, then you need to jump the signal and the 5-volt ref using that resistor and look for a change. It should change on the scan tool to 5 volts. Remember, you might need to crank the engine up for that to change. If we're, and this would be for circuit high, right? This would be for circuit low codes. Or you could say fixed at 0 volts. And really, this is what we had in section 7, so I didn't rewrite it here. This one, jump the sensor ground to the signal wire. You would do this one for circuit high codes or a signal that is fixed at 5 volts. That's when you would do that step 3. Final one on this page we didn't really talk about was the thermistors. The thermistor circuits are even easier. If you think about a thermistor, there is no harm at all in sorting out a signal wire on a thermistor. Why is that? Why is there no harm with a thermistor circuit? Because a thermistor circuit would be like this. You have the 5-volt source still from that regulator, but a thermistor has an internal resistor. And your thermistor voltage sensing circuit, it watches what it's sending out. So we call the signal on a thermistor the reference. And then we have a ground. If you have a circuit high code, that means the computer's seeing 5 volts on this sensor all the time. Are we safe to unplug the sensor and to ground the signal wire? In fact, what you can do, which checks them both at the same time, is you unplug the sensor and jump the signal to the signal ground. Use the ground to ground it. The computer should drop to 0. If that happens, how is your signal wire and how is your ground wire all the way out to that sensor? It's fine, and there's nothing wrong with doing that test. There is no harm in doing that because this circuit is designed to do that. That's what this resistor does inside. It's designed to cause a big voltage drop. That circuit's designed to be pulled to ground. So what I could also say is the reference circuit on a thermistor can be grounded. Don't ever ground the reference circuit on a potentiometer or a pressure sensor. Because look what's missing in that area on there's no resistor there. You ground the reference on a potentiometer or pressure sensor, you're going to short that 5-volt regulator out. You ground the reference wire, which is the signal wire on a thermistor, and you won't. The 5-volt reg's over here. It's protected by that resistor right there. Very quick test. What do you do on a thermistor circuit if you're fixed at 0 volts? The computer sees 0. Unplug the sensor. What should it read? As soon as you unplug the sensor on a thermistor, it should go to 5. If it doesn't go to 5, you have a wiring problem. If it goes to 5, how's your wiring? If you unplug this sensor and this jumps to 5 volts in the computer, whether you're using ScanDanner or a trouble code, what that tells you is this thermistor was shorted out and it was pulling the circuit to ground. So how is your ground wire? And how is your reference signal wire? They're both good. You unplug it, it goes to 5, you're done. These are some quick tests. Guys, I've used these hundreds of times over the years, and a simple scan tool, you're looking at the scan tool and you're unplugging a sensor and you're like, that sensor's bad. Just like that. Knowing what I'm telling you right here, you can do that. Thermistors. And you can take this even further. I mean, there's other sensors that act like thermistors that aren't really thermistors. I have a video on a GM fuel tank level sensor. That's really not a thermistor. Thermistor suggests temperature, right? Temperature changes the resistance of a component, and that changes the voltage. Certainly a fuel tank level sensor is not temperature regulated. It would be a float that sits in liquid that rises and falls that changes resistance. If you look at the wiring diagram for that circuit, it shows you something like this. Here's the diagram for it, something like that. What does that look like? Without looking at the internal computer parts, this section here would be a hinge. This would move up and down. There'd be a float attached to that. This is your signal wire. This is your ground wire. It is identical to a thermistor circuit, even though it's not. It works exactly the same as one. When the float moves, it's going to move this wiper up and down, which is going to change resistance on that circuit. The internal guts would be like this. Does that look familiar? Looks exactly like a thermistor circuit, doesn't it? So we can do the same type of integrity tests on the wiring for this design. And we did that. In that video, I suggest you guys watch it. GM fuel tank level sensor testing. I think that's what it was. This is what we're doing. I'll give you another example where we can do something similar if you know circuit designs. And this is a little bit out there, but a knock sensor. This is an example of a sensor that uses something similar to what a thermistor would do. That we're sending out 5 volts through a resistor. This is a voltage sensing circuit just drawn in a different way. So the computer's monitoring this circuit right here. If this sensor's unplugged, what happens is this 5 volts goes across the resistor and basically has nowhere to go. So what's the circuit going to read with it unplugged? It'll read 5. Why is that there? That's not part of the knock sensor circuit. It's there to make sure the knock sensor's plugged in. What a knock sensor does is it produces an AC sine wave in the presence of a spark knock. It's stressing a crystal in that knock sensor, and it produces its own electricity. So if you were to look at a knock sensor when there is a knock occurring, or if you take and you tap on the engine block next to the knock sensor with a pry bar, and you look at it on the scope, it actually looks like this. Every time you hit next to that knock sensor, it produces an AC sine wave. Some knock sensors will not have a bias voltage going to it. Some will. The ones that do, this is for diagnostic purpose. And what they do, so if you had your crystal sitting here, and this ground's on the shelf, they put a resistor inside that goes around this crystal to ground. And that resistor is designed to pull this signal voltage down to a certain level. And so let's say that this resistor plugged in, a normal number would be 2.5 volts on a GM on this knock sensor line. If this number drops, the computer sets a short circuit code. If that number increases, it sets an open circuit code. So why is it there? It's used for diagnostic for opens and shorts in the knock sensor signal line. If you understand what I'm telling you, circuit design, circuit integrity, you can take something like this, Here's a case study that I had. This was on I don't remember the vehicle, it was on a Chevy truck. The questions here would be this. I have a trouble code for a knock sensor. And the question for any code really is the sensor bad? Is there an open in the signal wire? Is the computer bad? That's really what you're thinking about. And this is what I saw. I had 4.8 volts on the scan tool all the time on that knock sensor. And I know the circuit design right away on this, I just showed it to you, and 4.8 volts is not normal. This uses a 5-volt bias. With the sensor plugged in, it should be pulling the circuit down, and it's not. So, computer wiring, here's your knock sensor. Computer's reading, let's just call it 5 volts all the time. Could there be an open in the signal wire causing that condition? If you think about the internals, remember the source, 5 volts supplied, there's a voltage sensing circuit that's monitoring it. If this is open, isn't this going to read 5 volts right here? Because there's nowhere for that resistor to drop voltage. There's no current flow, no voltage drop. So it'll read 5. Could be an open in the signal wire. Could it also be an open in the knock sensor, a bad knock sensor? Yes. Why am I not worried about a short to ground in this circumstance? If this wire was shorted to ground, the computer would be reading 0 volts all the time, and that's not what I have, is it? So I'm never worried about a short to ground on this one. I'm worried about an open in the wire or an open in the knock sensor. The test I did on this car is I just simply, and I didn't use my voltmeter, I'm just using ScannerDanner. I just simply went down to the knock sensor, I unplugged the knock sensor, and I grounded the signal wire. And when I grounded the signal wire, I monitored my scan data, and I went from basically 4 to 5 volts up here all the way down to basically 0 volts, 0.18. What's that tell me about the integrity of my wire all the way out to the sensor? It's good, and I'm done. So all I did was use a jumper wire and scan data and some common knowledge of circuit design, and basically I'm doing an integrity type test. I know this one seems to be kind of out of left field, that all of a sudden we're talking about knock sensors, but do you see the similarities in the coolant sensor circuit design, in the thermistor design, to what they're doing with this knock sensor? Electrically speaking, we can do the same kind of tests. And how fast was that? You know, I go to this garage and it has a knock sensor code. Actually, this was a beer distributor. I was doing a diagnosis in their parking lot on one of their delivery trucks. But I mean, I'm there, guys, for 5 minutes. I got a knock sensor code. They're worried about the check engine light. Of course, they don't know anything about the cars. They deliver beer, right? They're not mechanics. I'm looking at the truck. This is what I got. I'm on the car for how long? 5 minutes. Right? This is a nice, easy, paid job. And circuit design was key. Doing an integrity test was key. Knowing the circuit was fine within 5 minutes of working on it. Knowing it had a bad knock sensor. And there's more as we continue to go through this. There's other types of tests that are similar. But it is very valuable to save time, accuracy, and save time.